Hey everyone, I wanted to make a quick video going through a few different things from Unit 6 and also from some stuff I saw on some recent work you guys are doing. This first problem here it combines a few things. We've got a graph of a function here and it's g prime, so we got to make sure we're paying attention to that. So then we have g as a function where g of 2 equals 5. That's some function we don't know what it looks like, but it gives us essentially an initial condition. Okay, we've got the graph of the derivative g prime from -3 to 7. So it says to find the absolute maximum value of g on the interval -3 to 7. Okay. So one of the first things I want to say here is find the absolute maximum. All right, well that means I have to test out the endpoints, right? If we're finding the absolute maximum, it's not relative. We're not finding local max, local max. Local min. I need to find the highest point on this graph between -3 and 7. So we're going to make a chart, and I don't have a whole lot of room off below here, so I'm going to do a lot of this up on the side here to the right. We're going to make a chart that includes our endpoints and critical values. Well, what are the critical values? The critical values of g, again, we're finding the maximum value of g. So the critical values are where g prime is 0 or undefined. Okay, so I need to find where g prime of x equals 0 or undefined. Well, this graph is g prime of x, and so it's never undefined. But it is equal to 0. Okay, so g prime of x equals 0 when x equals -1, 1, oops, that's not right, 2, and let's see, 1, 2, 3, 4, 5, 6. Now, I am looking for an absolute maximum, which means the derivative would have to be going from positive to negative. G is going to go from increasing to decreasing. So my derivative has to go from positive to negative. Well, where's that happening on this graph? Well, this is g prime, so at -1, it's going from negative to positive. So this would be a possible minimum. So we can actually ignore that. Here at 2, it is going from positive to negative. So that's a good one. And 6, it's going from negative to positive. Right, I'm looking at just the y values. This is g prime, so that's out. Okay, so we only x equals 2 is only critical number where f prime, oh no, g prime, where g prime changes from negative to positive. So then I make my chart here. And I'm going to make a chart of my x values, my g of x values, and we want to label what they are also. So we have my endpoints, -3. That's my endpoint. I have a critical number, which is x equals 2. And then I have my other endpoint, which is x equals 7. So those are the 3 values I have to find. Okay. Then the next step is that I need to actually be able to evaluate what is g of -3, g of 2, and g of 7. And that's where this comes in. Well, look at that. G of 2 is 5. Perfect. I have one of them. But how do I use that to find the others? Okay. This is where our second fundamental theorem of calculus comes in. So we've got this kind of formula that we need to be able to know and use. It's going to come up almost certainly. Okay, and that's this. If we have the integral from a to some value of x of f prime of t dt, the integral of the derivative gets me back to the original. So it's going to be f of x minus f of a. And that f of a is like my starting initial value there. So that's our fundamental theorem of calculus, right? Just plugging in the top, plugging in the bottom, and when we know the antiderivative. So here I can then solve this as f of x is going to equal the integral from a to x of f prime of t dt plus f of a. And so since I know f of a, that becomes kind of our initial condition here. So how does that work here? Well, I can write a function for g of x then. This is saying I can write a function for the original function if I have the derivative here. So g of x is going to equal the integral from a, well, a is going to be the x value I know, 2 to x of g prime of t, I can't use x again, so that we just switch it to t, dt plus f of 2. Okay, well that f of 2 we know is 5, so plus 5. And then I can evaluate this. So g of negative 3 is going to equal the integral from 2 to negative 3 of g prime of t dt. Okay, so then I just have to use the graph that I have a graph for this. The integral from 2 to negative 3 of g prime of t dt. I look at my graph over here. Here's 2, here's negative 3. So I just need those areas. So pause the video, calculate those two areas, and I'm going to put them up on the screen here. So you should get, so for this first triangle here, that area 1/2 base times height, you should get 3/2. For the green triangle here on the left, we should get 4. Okay. Now, if I'm taking the integral backwards from 2 to negative 3, right, my areas are going to count as opposites. So this one would be negative 3/2, and this would be positive 4. So I'm going to have equals negative 3/2 plus 4, and then I still have this plus 5 there that I didn't write that time. Okay, so I have, what is that? Negative 3/2 plus 4 plus 5, so 987.5 would be my value there. And then I'm going to do the same for 7. Okay, sorry, I'm running out of room here. G of 7 is going to equal the integral from 2 to 7 of g prime of t dt plus 5. And same thing, we'll find those areas, so that'd be from 2 to 7. So when you work that out, you're going to get this area is 4, and this area is 1/2. So from 2 to 7 here, we're going to have negative 4 and positive 1/2. So that's going to equal negative 4 plus 1/2, and then plus the 5 that was there. So that's negative 3/2 plus 5 would equal 1/2. So 1.5. Okay, so all that allows me to say that, and this chart is my justification. You can use a candidate's chart to justify an absolute maximum or minimum by saying that the absolute max of G is 7.5 at x equals negative 3. Alright, the rest of this I want to try to go through quickly. I say that every time and it never happens, but we'll try. Using some second fundamental theorem of calculus, this is the idea that if we have a function that equals an integral, and we want to take the derivative of that function, then it's literally plugging in the top bound to there, and then if it has a derivative, we have to do chain rule. Okay, so all of this allows us to do things like finding maxes, mins, dealing with increasing, decreasing, concave up and concave down. And so here's a quick example. Given g of x is this integral, find g prime of x. Okay, well, g prime of x is going to equal, you plug in the top bound here, so we'd get t cubed would become x squared cubed minus 4 times x squared, and all of that would need to be multiplied by the derivative of x squared, so by 2x. And so to simplify that, we'd get x to the 6th minus 4x squared, all of that times 2x. And again, so you could leave that unsimplified, you should, but what do we get? 2x to the 7th minus 8x squared. Okay, how would you determine if it was increasing, decreasing, concave up, concave down? You'd be looking at the derivative. Is the derivative positive or negative there? Well, is this value here positive or negative? Concave up or down, we would take the second derivative, etc. Okay, moving on a little bit more, we've seen, this is the formula essentially that we saw up above. So finding a future value of x, you must know an initial value of x and then use the definite integral to find the accumulated change from a to b. Okay, so example 1, we're given f of 5 equals 2. Find f of negative 3 if we're given this integral. So the way I'd approach this is, knowing the integral of a derivative, I know I can evaluate this. I can say that f of 5 minus f of negative 3 is going to equal negative 14. F of 5 I'm given as 2 minus f of negative 3 equals negative 14. And so subtract 2, divide by negative, I'm going to get f of negative 3 is equal to positive 16. Finally, we're going to do a couple quick u substitution problems. I'm not sure where this would come in necessarily because of the resources you'll have, but it's still that they'll probably find some way to assess this. So here, remember, u substitution. So we're taking the integral, and what I want to do is find something where I can plug in u and have the derivative of that thing that I make u show up on the outside. And so I have this u equals x squared, and so we'll say du equals 2x dx, and I just want x dx, so I solve this and I get 1/2 du equals x dx. Then I can make my substitution. I can say that this is going to equal the integral cosecant squared of u, and then x dx is du, and I need the 1/2 that can go in front. To solve this, you're just going to ask yourself what function has a derivative of cosecant squared, and I know the derivative of tangent is secant squared, so derivative of cotangent is negative cosecant squared. So this is going to equal negative 1/2 cotangent of u plus c. And then I can plug my u back in, negative 1/2 cotangent of x squared plus c. In example 2, we have a similar problem, but for this one, we have bounds from 0 to 3. So when we set up u equals x squared plus 16, we'll get du equals 2x dx, and I want x dx, so 1/2 du equals dx, x dx. And so now I'm going to set up my integral. And we've got 0 to 3. So those are x's I need u's. So you plug back in here, and you basically say, all right, if my lower bound is x equals 0, that's going to give me u equals 16. That's my lower bound. I'm just plugging into here, like 0. And then my upper bound is x equals 3, so that's going to lead to u equals 3 squared, 9, 16, 25. Okay, so then plug the rest of this in. I have my x dx, which is 1/2 du, so the 1/2 is in front, du. And I'm going to end up with 1 over root u, so I'm going to call that u to the negative 1/2. So now we go 1/2 times integral of u to the negative 1/2, add 1 becomes u to the 1/2, and multiply or divide by the new exponent, so really times 2, from 16 to 25. And the nice part about this is we don't have to plug the x squared plus 16 back in. We can just evaluate because these bounds are in terms of u. So it's 1/2 times 2 root 25 minus 2 root 16. That's nice and easy. 1/2, 2 times 5 is 10, minus 2 times 4 is 8. 1/2 times 2, my answer is 1. Nice. Okay, last problem here. If it gives us u, it says u is the square root of x, how can you represent this integral in terms of u? So right away I'm kind of thinking I should probably find the du. So I know this is u equals x minus 1 to the 1/2, so my du is going to equal 1/2. After taking the derivative, x minus 1 to the negative 1/2 dx. In other words, that's du equals 1 over 2 root x minus 1 dx. And that sort of seems problematic because that doesn't really fit nicely in here. But hey, let's see what happens. Okay, so I'm going to write my integral, and I know I need new bounds, so let's plug in. This is 2 for x, so x equals 2 leads to u equals 2 minus 1 is 1, so u equals 1, square root of 1. And then x equals, what's my upper bound? 5, leads to 4, square root of 4 is 2. U equals 2. So I know my bounds are from 1 to 2. And so we're trying to write everything in terms of u. So I've got on the top square root of x minus 1. That is u. But I have this bottom of the fraction as x. I can't write it in terms of x. I need to somehow, I guess, get x in terms of u. Well, we did a few like this, where I'm going to take that equation for u and solve it for x, so that I can get x equals stuff with u. So we would square both sides. U squared equals x minus 1. That's going to give me x equals u squared plus 1. Cool, that's my bottom, u squared plus 1. And then I have dx. I can't write dx, I need du. So again, I have an equation that involves dx and du. And so I can take that and solve that for dx, because I want to replace dx. So here I've got dx is going to equal 2 root x minus 1 du equals dx. Great, except it still has root x minus 1. But wait a second, I know what that is. Root x minus 1, that's u. So this is 2u du is equal to dx. So for my substitution here, I would say d2u du. And usually you wouldn't write it like that because I can actually multiply this together. So to get a final answer here, I'd get 1 to 2 of 2u squared over u squared plus 1 du. And notice the problem just said, write it is a definite integral in terms of u. That's what we've done. Changing the bounds, super important. You had to get that done. All right, that's all for this video. Thanks for watching.